Okay, so today in this video, I'm going to show you how to use your molecular models. It's going to be very important for you to see this demonstrated because right now all you have is just a box of pens and straws that look like this, and it's going to be very important for you to understand what you're trying to see with these things. So the simplest molecule that we're going to look at is first going to be ethane. And here you're going to need to be able to look down the carbon-carbon bond. You're going to make your ethane like this. You're going to have to be able to look down the carbon-carbon bond like a Newman projection, okay? And so you're going to have to be able to see the rotation about the carbon-carbon single bond. I'm going to show you over here on the overhead document camera because I think it will be a little bit easier to see it here if I position it just right. Yes. Okay, so once again, this is ethane. Here you can see the carbon-carbon single bond, the six CH bonds, and you can see I've positioned this so it's the same as if you are looking down the carbon-carbon bond. And so this is what a Newman projection looks like. So you've got the carbon, the CH3 in front and the CH3 in back. And when you look down the carbon-carbon bond, you can see I have them positioned right now so that all of the CH bonds are eclipsing. This is the eclipsing conformer. Okay, conformers are not isomers. Okay, it's the same molecule, just with the bonds rotated some. So isomers are two different molecules. This is the same molecule with just rotation about the carbon-carbon single bond. And this rotation about the carbon-carbon single bond is going to be going very, very rapidly at room temperature, just like a propeller on a plane. This is going to be going around. And so you're going to have the eclipsed conformer, which you can see here. And you need to make these. Don't just rely on looking at mine. You need to make these and touch them, just like I am right now, and hold them up and look down the carbon-carbon bond and see it for yourself so that you become very comfortable with these things. And so there's eclipsed, here is staggered, and you can see. So the eclipsed form is going to be higher in energy because you have the electrons in the CH bonds repelling each other, and they are closest together in this conformer. So now let's set aside ethane, and we will graduate to propane. You can see that this is C3H8, and you need to make this C3H8. And when you do, then you're going to look at the Newman projection once again, and you're going to look down the carbon-carbon bond, and you can pick one, either this one or that one. They're the same because the molecule is symmetrical. So let's just pick this one. Here you're going to have a little bit more complicated situation. There, I got it. Okay, now it's eclipsing. You can see that you have the two CH bonds eclipsing here, the two CH bonds eclipsing here, and you have a CH bond eclipsing a carbon-carbon bond. And so you can have, this is going to be the eclipsed conformer, and then you're going to have staggered, where the CH bonds are as far away as possible from the other CH bonds and the carbon-carbon bond. And so the angles here, the dihedral angles, are going to be 60. Okay? Dihedral angles, the torsional angles, sometimes it's called. And so once again, you're going to have re-rotation, and you need to put this together and move it around in your hands, just like I am. We'll discuss this also in class when I go over the PowerPoints, but I wanted you to see this because just looking at the pictures does not really explain this quite well enough. And then another molecule that we will discuss will be butane. Okay, so this is C4H10. And here, the carbon-carbon bond that we will be interested in looking down is the one I'm pointing at. It is from C2 to C3. Okay, C2, C3, carbon-carbon bond. And now you can see that I'm putting this like it's a Newman projection. We're looking down the C2, C3 bond, and you can see the rotation. So this was eclipsed, staggered, eclipsed, staggered, etc. Eclipsed, staggered, eclipsed. Now, I might point one thing out here, and that is that this eclipsed conformer is going to be the least stable of all the conformers, because here you have the two metals eclipsing each other. And so you're going to have the greatest steric hindrance in this conformer. So this conformer is going to be highest in energy. And similarly, if we go to this staggered conformer where the two metals are as far apart as possible, this is going to be the most stable. So this is the most stable conformer because the metals are as far apart as possible. And this is the least stable conformer because the metals are eclipsing. So those are the exercises with the models for the linear alkanes that we're going to look at. We're not going to look at any other linear alkanes. However, we are going to, in a separate section, cover cycloalkanes. So let's look at those now also. And you'll have to make these as well. You'll want to. Here is cyclopropane. You can see how strained it is. Look at how the bonds are straining. This molecule is just ready to fly apart. And indeed, this one of the bonds does open very easily, more easily. The carbon-carbon bonds in cyclopropane are weak because they're so strained. And if you look down the carbon-carbon bond here, you can see that you have total eclipsing of the CH bonds. Okay, as you look down the different carbon-carbon bonds, you can see you have total eclipsing all the way around, and that makes this molecule, that adds to the instability of it. So it's not just the angle strain, it's also the torsional strain. Because what happens is cyclopropane does twist just a bit to try to get rid of, my molecule is going to fly apart, I'm afraid, to try to get rid of some of that eclipsing. And so it will twist a bit to try to remedy some of that eclipsing, the way that I'm sort of pushing on it with my fingers now. Okay? Now you have also cyclobutane. Here's cyclobutane. You'll want to make cyclobutane. You want to make all of these and handle them just the way I am here. And so if you look down look at the Newman projection, look down the carbon-carbon bond, in cyclobutane, you'll see, once again, there's eclipsing all the way around. Okay, all the way around as you go around. And so there is something that cyclobutane can do in order to get rid of that eclipsing, and that is it puckers a little. You can see how I've puckered that? It's no longer flat. The four carbons are not in the same plane anymore. And so it is no longer flat, and by puckering it a little bit, you do release some of the eclipsing. So the puckering costs a little bit in energy because the bond angles here are compressed a little bit. They're made a little bit smaller by the puckering, but you get that more energy by relieving, more stability by relieving the eclipsing. Then we go on to cyclopentane, and here we I'll start out with it being flat, and you can see the same thing, and I haven't put all the CHs on, but you can see the eclipsing here. And so what happens with cyclopentane is, once again, it puckers a little bit. It does not stay flat, as you can see. It puckers a little bit. And so this conformer with the puckering is called the envelope conformer. And you can, if you look at it, you'll see it looks sort of like an envelope. This would be the flap of the envelope, and this would be the envelope itself. And it sort of resembles what an envelope might look like if you just simply threw an unsealed envelope out on the table. And so you'll want to put your molecular models together and look at them like this. And some of the things that you'll read in your textbook, you'll be able to see them when you look at your models like this. Here you do still have some eclipsing. You can see the eclipsing, but now you've rid some of the eclipsing here by that puckering. Now, the cyclohexane is the last of the cyclic molecules that we're going to discuss. Cyclohexane is a little bit more complicated. It has exactly the ideal angles all the way around, and so it's a very stable cycloalkane. But the important thing that you must see by the models, and so this is what I'm going to show you here, is that the cyclohexane exists in a chair conformation. It is certainly not black. So let me show you this. You can see the chair conformation. If you look at it, this would be, you can see, yes, the chair conformation. This might be where you would put your feet down here, and up here would be where your head would go. Okay, and so this would be the seat of the chair. So this is the chair conformation. And there's another conformation that's higher in energy, which is a boat. And we get there by doing a partial ring flip. And you'll have to just do this in your hands, get your molecules out and do a ring flip, and you'll see that this then becomes a boat conformation, where you have both of these carbons going down, and then this would be the two ends of the boat, and this would be the boat itself. Okay, so make your molecules and get so that you can do these ring flips. I'm going to put this back in the chair conformation because there's something that I want to show you. The chair conformation can interconvert to another chair conversion, to another chair conformation. So it does this, what's called a ring flip. And I'm going to show you that ring flip. And when I do the ring flip, you're going to see something striking happen to these CH bonds. Notice how the CH bonds are all sticking out. when I do the ring flip, so that this goes down and this comes up, what happens to all those CH bonds is now they are all sticking either up or down. Now they are in what's called the axial position. Those CH bonds are in the axial position, and you'll see this drawn in your textbook many, many places. And so you'll see many examples of the drawn cyclohexane with all of the CH bonds or all of the substituents in the axial position. Let me go back to the other chair conformation. Here we are, where all the CH bonds are sticking out now. These are called equatorial positions. So when the CH bonds are sticking out, they are in the equatorial position. When they are sticking up or down, they're in the axial position. Now here, you'll notice that there are CH bonds in the axial position. I just didn't put them in here. 1, 2, 3, 4, 5, 6. But I wanted to show you the ring flip with just 6 of these on here so that it's very striking. You should make this and go through this and get so that you can do this by yourself. You simply have to push this end down and this end up, and you can do that ring flip. You should get so that you can do that yourself. I think this is the essential part of what you need from your molecular models. The only last thing I might point out is that whenever you have substituents in the axial position, you'll notice how close these are. Substituents in the axial position will be very close, whereas substituents in the equatorial position will be far away from each other. And so when you have substituents in the axial position, there's a lot of steric interaction here, and these are called 1,3 diaxial interactions. If you'll count down the carbon ring, 1, 2, 3. So these two substituents, and then here they're just hydrogen, so it's not significant here. But if you had a couple of methyls here, this would be a very significant 1,3 diaxial interaction. 1, 2, 3. So this one would be in the 1 position, this would be in the 3 position. So it's called 1, 3 diaxial interactions. So I urge you to use your molecular models and make these and play with them in the same way that you've seen me play with them here. I hope this helps you.